Okay, team, physics team, here we are in our last week and our last topic, and it's kind of a fresh topic, so I hope you enjoy this. So I'm going to try and do two videos. I'm going to do this one on an overview, and then the next one to come later, I'll try and focus specifically on the assignment. So it's been a long semester and we've dealt with some unusual circumstances and some of you probably feeling exhausted. That's the way I feel sometimes. But I hope occasionally you feel the exhilaration of everything you've learned, and many of you have come a long way and have really performed amazingly well and really learned material that I think at the beginning of course you would have felt challenged that you could have ever learned. So here we are in our final week, and this is chapter 11 out of the book. There's 20 pages. It covers everything I have listed here, and you might want to use it for reference. I'm going to go through a lot of material rather quickly here, but this is a video, so you can pause, you can back up, you can just watch the video and try and absorb some of it, and then do some of the assignment and come back. You can look at certain sections. So I hope having the video available for you is a good study aid for you. Okay, so here are the topics we're going to cover. States of matter, solids, liquids, gases, and plasma. So you're familiar with the solids, liquids, and gases. Plasma includes a state that we're not so familiar with, a high energy ionized gaseous state, like the state of the sun or the state inside of fluorescent light bulbs, and a few other examples that we're familiar with. These are all the 4 different states that matter comes in, and we'll discuss those in some detail. Then we need to be familiar with the concepts of density. We did that the first lab. This is the symbol rho. It's the symbol we use for density. We don't use D. And it's the ratio of mass to volume. And so it has units of kilograms divided by meters square, or sometimes for convenience, because it's a more, tangible scale, we'll use grams and centimeters squared. Then we move into the concept of pressure. And pressure is a force concept, but it's different from force in that it's force divided by the area. So it has units of newtons per meter squared. That unit is given a name. It's called a Pascal, and when it's written out, it's uppercase P, lowercase a. A Pascal, you'll see, is a tiny amount of pressure, actually, because 1 Newton isn't much force spread out over a whole cubic square meter. Imagine how big that is a very low pressure. So the pressure due to our atmosphere example is 100,000 pascals. We'll be looking at that in some detail. Then we want to look at the pressure due to fluids and how that varies when we have fluids in a container or under different circumstances. And this is the equation for that. The pressure in a fluid depends primarily on the height. Well, it also depends on G, but if we're on the surface of the Earth, that doesn't vary. That's a constant, 9.8. And it depends on the density of the fluid. So the pressure that we feel due to the air that we live in, the atmosphere, is great only because the height is very great, but the density of air is low. Whereas if you dive into a swimming pool and you go down 10 meters, then you're subject to a pressure which is twice the pressure of the atmosphere, because the water is so much more dense. The pressure changes with height very rapidly. Whereas if you climb the stairs in your house, the atmospheric pressure doesn't vary much. But if you go up to the top of a mountain, then the pressure varies. So that's that equation. Pressure due to a fluid is the density of the fluid times G times the height of the fluid. You'll use that equation a lot. And the final, actually it's not, it is the final equation, yes, is what's called Archimedes' principle, or the buoyancy force. So when we put things in water, they may float, they may sink, they may weigh different amounts, and that is the force of the fluid on the object. It's called the buoyancy force. We'll label it FB or B. And when you look on your equation sheet, you'll see all these equations. There's three forms of the buoyancy force, also known as Archimedes' principle. Okay, so when you hear Archimedes' principle, we're talking about this. And it's simply the weight of the fluid displaced. So if you put an object in water, it displaces, the weight of the water it displaces is the buoyant force. If you put it in air, the weight of the air displaced is going to be much less, so the buoyant force in air is less. So we float in water, but we don't float in air because of the difference in density. So the weight of the fluid displaced, which is the mass of the fluid displaced, that's the FD times G. But if we replace the mass of the fluid displaced with the density and the volume, we get this equation, which we use a lot. The buoyancy force is the density of the density of the fluid displaced times G times the volume of the fluid displaced, Archimedes' principle. Okay, so that's the overview of what we're going to do. Now let's dig in and step through each of these 5 items in a little bit more detail. Okay, the 4 states of matter that I mentioned. Unfortunately, this figure is a little fuzzy, but I'll walk you through it. There are the 4 states: solids, liquids, gases, and plasmas. So the solid, all the atoms and molecules are bound together, and it has a rigid structure. We understand that. And then a liquid, all the atoms and molecules are loosely connected. So they stay together, but they can flow around each other. And in a gas, all the atoms and molecules are separated. So you see a liquid, this gives us an important property. A liquid is hard to compress. Solids are hard to compress. In fact, for our purposes, under normal pressures, we consider a liquid can't be compressed. With a gas, there's a lot of space between the atoms and molecules, so it's fairly easy to compress gas. When you push on a pump, you take the gas in the pump and you compress it quite a bit. And a plasma is just a gas at very high temperatures where the atoms and molecules are ionized, right? Ionized means that the electrons on some of the atoms are removed, and so they're charged particles. And this is all temperature related, right? Temperature or energy related. If you take ice and you apply temperature, it becomes water, and if you keep applying temperature, it would become a water vapor. And if you put that water vapor in a high temperature furnace, it would become ionized glowing plasma. Okay, I have one more. Okay, I uploaded one more figure. Equally hard to read. Solid, liquid, gas, plasma. The picture's pretty similar, and I realize I thought I would have this because you could maybe read through this, but it looks like it's probably too fuzzy for you to read. But I'll put it here, and if you want to try and read it, you can pause the video. I can kind of make it out a little bit. So, but I think it says pretty much what I already said. Okay, here's our concept of density. There's the equation I showed you. Remember, this symbol is called rho. It's the lowercase Greek letter rho, and it's the ratio of mass to volume. And if we measure the mass in kilograms, we'll measure the volume in meters cubed, right? A volume is 3 dimensions, like length times width times height. If we measure the mass in grams, then we'll measure the volume in centimeters cubed. And this table of densities here has the grams per centimeter cubed. So it's useful. I think it's important that you visualize these things. So a cubic meter, you know what a meter is, it's a little bigger than a yardstick. That's a big volume. So if we take water, for example, which is our reference, to three significant figures, it's not exactly one, but it's the three figures, it's 1 gram per cubic centimeter. And picture a centimeter, it's like a little tiny box, like the end of your finger, little finger, and it weighs a gram. And so that's just convenient. And it's a reference. So when we think of water as 1, not surprising, we have wood as 0.85. Actually, that's a fairly dense wood. Pine would be about 0.5, about half the density of water. You see that air is only about 1,000th the density of water. So it takes 1,000 times more volume of water, of air, to equal that of water. But still, if you take the air that fills the refrigerator, it would be a kilogram or more. So it's not insignificant. And then from water, we see ice is a little less dense. That's why ice floats. We see ethanol and methanol are a little less dense, so they float in water, although they mix with water. So most fluids are less dense than water, but there are some that are more dense. When we move into the solids, they're definitely more dense. So we take a low-density solid, it's 2.7 times more dense, and we take the most dense solid on the list, and it's almost 20 times the density. Lead, okay? And if you remember back to the lab, the copper and the iron were about 8 or 9 times the density of water. So it's good to just have a familiarity and a sense of what the density of things is, and we often compare it to water. However, if we go from grams, right, a little box that's a cubic centimeter is a gram. Supposing we go to this big meter, it's going to be 1,000 kilograms. So let me write that down. 1,000 kilograms, that's a lot. That's 2,000 pounds. That's a ton in 1 cubic meter. But think about a cubic meter. It's a huge amount. And so converting units is a little bit tricky because of this cube. You'll see that when you're doing the assignment. You got to be careful when you're converting units from centimeters. You got to cube this thing, because 1 centimeter is 100. 100 centimeters is 1 meter, but 1 cubic centimeter is only 1/1,000,000th of a cubic meter. So just keep that in mind when you're doing units conversion. Okay, we talked about pressure. So here's our pressure equation. Pressure is force over area. So it has units of newtons per meter squared. We generally don't mix the newtons with centimeters squared because newtons have meters in it. So try to stick to these units. And that's often called a Pascal, uppercase P, small a. It's the name of a person, and lowercase is a unit, Pascal. And this shows you this down here. And if you had this block weighing 100 newtons lying on its large face, the pressure would be less than if you stood it up on its smaller side face. You see the pressure here is 1,000 pascals, and here it's 10,000 pascals. Remember what we said earlier, the pressure due to the atmosphere is 100,000 pascals. So the numbers in pascals are often going to be quite large, generally in the thousands or higher. Okay, pressure due to a fluid. I think we all have a good intuitive sense that pressure depends on depth. So if we had this water tank and we punched a hole here, it's going to squirt out a lot more than here because the pressure down here is greater. And if you go into a swimming pool or you go diving, the deeper you go, the greater the pressure gets. And even the atmospheric pressure, which we often don't think of it because we live in it, depends on where we are in the atmosphere. So if you go up in a plane, the cabin is pressurized because there's not enough air pressure, or even if you climb a high mountain. So pressure, and so we have this equation that pressure depends on the density of the material times G times the height. So the G doesn't vary as long as we stay close to the surface of the Earth, and so it'll depend on the density and the height. Like I mentioned earlier, air is very low density, so it takes a lot of height in order to change the pressure much. It won't change much climbing up a flight of stairs, but in a swimming pool, as you go down, you can feel the pressure change very dramatically because of the high density. So this is the equation that we're going to be using whenever we run into a situation. And remember, what's causing the pressure is the weight. So if this were a water tank and you're going down, there's more water pushing down on you the deeper you go. And that's what causes the pressure. The force, right, is the weight of the water, and it's the area over which it's applied. So you could calculate the pressure at the bottom of a swimming pool if you knew the depth of the water and the density of the water, and so on. Okay, I just realized I forgot something in our list. So I think you can see this. If you go back here, we talked about pressure. We talked about pressure due to a fluid. Before we go to Archimedes' principle, is one other thing called Pascal's principle. And let's talk about that. Pascal, it's called Pascal's law here, but I call it Pascal's principle. There is a section in the textbook on this. So what Pascal's principle says is that if the pressure in a fluid is increased, if you increase the pressure of the fluid anywhere, that pressure increase transmits through the fluid. So if we had, like in this situation, if we had pressure gauges at all different points along this system, if we push down here and we increase the pressure, say, by 10 pascals, every pressure gauge everywhere would go up by 10 pascals. So a pressure increase here is transmitted undiminished to here. And it's Pascal's principle that is underlying a lot of hydraulics in different situations. So let's take a look at a typical application would be a hydraulic lift for a car. So since pressure is force times area, if we increase a little bit of if we increase the force here, that's divided by a small area, the pressure goes up. So like pushing on a hand pump. It's a very small tube, and you exert a force. That pressure increases by the same amount here, but since the area is much bigger, the force is much bigger, right? Because the idea is if you make, here's our pressure equation, it's the ratio of force to area. So if I make the force 10 times greater here, but the area is 100 times greater here, then the pressure's the same, but the force here is also going to be 100 times greater because it's the same pressure. And so we use this. This will show up in the assignment, Pascal's principle, to figure out, like in any given situation, what that would mean. So in simple terms, it's kind of like using a pulley where we can increase our force. We can increase our force. It's a force multiplier. Okay. In other words, just consider this. Let's say this is 1 centimeter. Then the area would be 1 centimeter squared. If this is 10 times 10 centimeters, but the area then is going to be 100 times bigger. If this is 10 times bigger in diameter, this is going to be 100 times bigger. And so a force of 100 newtons here is going to be a force of 10,000 newtons here. That's how it works. These equations will show you that, and there is 1 or 2 problems in the assignment related to Pascal's principle. Okay, a few words about Archimedes. I just looked him up. Archimedes of Syracuse was a Greek mathematician, physicist, engineer, inventor, and astronomer. He was born in 288 BC and died in 212 BC, so 2,300 years ago. The story about Archimedes is that he was given the task of figuring out whether the king's crown was gold or some fake metal. And as the story goes, he's lying in his bathtub, noticing how in the bathtub he weighs less than he does out of the bathtub. That there's this force of the water, this buoyant force on him, and he came up with the idea that, oh, if I weigh less in the water, the crown's going to weigh less in the water, and how much it weighs less in the water is related to its density, and through that method I can figure out whether it's gold or not. And when he had that insight, he claimed Eureka and jumped out of the bathtub. So that's the story of Archimedes. And what we know about buoyancy is that the buoyancy of an object is related to its density. And so that if something is less dense than water, it floats. And if something is more dense than water, it sinks. And in the unusual case where something is exactly the density of water, it will stay suspended. And even when you look at these pictures, you can get a sense, oh, this is like a piece of cork. It's very low density because it's floating high. And this is probably a piece of wood because it's floating about halfway and sinking about halfway. What's not always obvious is that when an object's in water, even if it sinks, it weighs less in water. And here's a demo that I would do in class if we were in class. I would take a weight and put it on a scale and see how much it weighed. So let's say this weighs 7 pounds. Let's call it newtons because that's what we're familiar with, 7 newtons. Then I put it in the water and the scale drops. You see there is a buoyant force on it. It drops by 3 newtons. It drops to 4. And what I notice is that if I fill this to the top, so the water's about to spill out, I put this in here and I spill that much water, it ends up being 3 pounds of water. So there's where the notion comes from that the buoyant force, which is 3 pounds, right, because there's 3 buoyant and 4 scale make the 7, the buoyant force is equal to the weight of the water displaced. And we can actually use that, as Archimedes did, to find the density of this object. I'll show you how. Okay, here's the shortcut way of doing it. So we see that the density, the volume of the object and the volume of the water are the same, because that's how much water spilled, right? So the density of water is 3 pounds by that amount of volume. And the density of the object is 7 pounds I forget the pounds, by that amount of volume. And so if we compare the density of the object to the density of water, we would have 7 pounds divided by the volume. This would be 3 pounds divided by the volume. It's the very same volume. And so we can see that the density of water is 7/3 that of water, or 2 1/3 times the density of water. Okay, one more thing on Archimedes' principle. It's useful to understand why there's a buoyant force when you put something in water. And this is, so when something is immersed in water, the pressure, one of the things about pressure is it acts in all directions, right? It just doesn't go up, it goes down. So at the top, the pressure of the water is pushing down on the object. At the bottom, it's pushing up, and at the sides, it's pushing in. So it's being compressed in all directions. But because pressure depends on height, the pressure at the bottom is higher than the pressure at the top. And so there's a net force up. That's what causes the buoyant force. And it doesn't matter, really, whether the object is round or has any shape. If we take this object and we look at it, it's going to be the same way. This is immersed in water. The pressure at the top pushing down is going to be less than the pressure at the bottom pushing up. And so there's a net upward pressure and a netward force, and that's what causes the buoyant force. And we can see that in a more diagrammatic way here. And if we actually calculated, we could actually calculate this. In fact, one of the problems in the assignment will walk you through this. If we took the size of this cylinder and we calculated the area at the top and the pressure at the top, we could figure the force at the top. And we take the area at the bottom and multiply that by the pressure, then we would get the force at the bottom, and we would see that the difference in these two forces is in fact the buoyant force on the object as predicted by Archimedes' principle. Okay, one more thing before we stop. Okay, we're almost done. So back to our original list of bulleted things that we've gone through over the past half hour. Remember, I missed Pascal's principle. We talked about that earlier. The final thing is Bernoulli's principle. This is actually found in chapter 12. This chapter 11 in the textbook is on fluid statics, and this is a fluid principle that involves the flowing fluids. So Bernoulli's principle, you'll find it, if you want to read about it, in chapter 12. So in the assignment questions, you'll see a lot of questions where it asks you to identify these various principles, and here are the applications of Bernoulli's principle. So formally what it means is, supposing we have a pipe that's constricted and the water's flowing through this pipe, but when it gets to this constriction, it has to speed up, right? Because it's forced through there faster, and then it slows down when it comes out the other side. And so as this liquid force through here speeds up, the opposite thing of what you would expect happens. As the flow velocity increases, the pressure in this area drops. So when fluids flow very rapidly, there's a drop in pressure. And here are several applications that show how this works. One very important and useful application of Bernoulli's principle is the airplane wing. And so airplane wings are designed so that when the air flows over the wing, it has a longer distance to go, and so it flows faster over the top than it does over the bottom. So airplane wings aren't made in a symmetric way. They're made in a way that forces the air to flow faster over the top. And the result is, by Bernoulli's principle, when the air flows faster over the top, the pressure on the top of the wing drops, and actually the wing, we call it lift, but it's actually the pressure at the bottom is higher and the air is pushing the wing upward. That's the lift force of wing design. That's one application of Bernoulli's principle. Another application that you may be familiar with, because we all do a lot of driving, is when you pass a truck nearby, it almost feels, maybe you think you're being fooled, but it almost feels like you're being drawn toward the truck. And the reason is that's actually true, because when the wind flowing between you and the truck, you're close to the truck, gets squeezed in, it actually speeds up and it lowers the air pressure here. And so both the truck and your car have a net pressure pushing them towards each other. So that's a very real effect that you feel on the highway, and another application or demonstration of Bernoulli's principle. We all know that in hurricanes and tornadoes, roofs are often blown off houses, and we tend to think of the winds lifting the roof off the house, blowing it off because of the high speed of the winds, but that's actually not what happens. You see high winds go over a rooftop. That means the wind is moving very fast. The pressure on the roof is actually lowered, and so the pressure inside the house becomes much higher and the roof gets blown off. It's shown in this diagram. You see the pressure on the roof from the fast-moving air is reduced, and so the static air inside is at a much higher pressure, and so the roof actually gets blown off by the high pressure inside rather than the wind tearing it off by physically lifting it off. And finally, here's two things you can do at home, and I encourage you to do them. If you can find 2 straws or a straw that you cut in half, fill a glass almost full of water, stick the straw so it's sticking up over the top, and then take the other straw and blow across the top of the straw, and the liquid will rise in the straw and spray out. It's actually how a paint sprayer works. So what happens is when you blow across the top of the straw, you lower the pressure in the straw, and the atmospheric pressure pushes the liquid up the straw. It's actually the same thing that happens when you suck on a straw. We think we suck on the straw and we pull the liquid up, but think about it. You can't pull liquid. When you suck on a straw or you blow across the straw, you lower the pressure, and it's the atmospheric pressure that pushes the liquid up. If this were in a closed container, it wouldn't work. You can't suck liquid out of a closed container. It has to be open. So that's not only Bernoulli's principle, but the idea of suction. So try this. And the last final thing, this is something I just found. I never even knew about this. And you should do this right now. Get a piece of paper, fold it like this so it's like a little tent, and stand it on the table in front of you, and stick your mouth right up at the opening. Get right in at the opening and blow through this. This is the reverse of the hurricane situation. And when you blow through there, what's going to happen? The air is going to rush through. There'll be a low pressure area. The high pressure area is now outside the house. And you can guess what's going to happen. Go ahead, get a piece of paper and try it right now.